So in this lesson, we're going to go over how PLCs store information and the different ways they can represent that information. Just like for us to communicate, we need to have a common language. In this case, I'm speaking English and you're able to interpret it. And that English is made up of sounds that we represent with different characters, and that's our alphabet. To store information in a PLC, you need to be able to understand the alphabet that it's working with so that you can then interpret it and get meaning out of it and understand what's going on. So some of the background on that would be, how do PLCs make decisions? What's going on inside the processor that's at the heart of the PLC? So like pretty much all computers, the processor inside the PLC is made up of thousands and actually millions of transistors. And so transistors are electrical devices. You can think of them basically like relays that you're familiar with, only instead of having moving contacts, they're a semiconductor device that, based on the presence or absence of a voltage or current, it lets an additional voltage or current pass through it. So it's a switching device. And so its value can either be on or off. In our case, we typically represent an on as a 1 and an off as a 0. So if you kind of think of that as what we would call a binary system. So what I mean by binary is bi, meaning two options. So in this case, if you have one storage point in a PLC's memory, it can have two values there, either a 0 or a 1. That's different than how we keep track of numbers normally, right? If we think of our decimal system, so in the decimal or base 10 system, any single character can have a value of 0 to 9. So you can see that the information density, or however you want to say that, each character can have a lot more options in a decimal system than in a binary system. This binary, 0 or 1, decimal, 0 through 9. There's other systems that actually used to be quite common in different PLCs. One of those might be an octal system, and in that case you could have 0 through 7, 8 different characters. So octal, base 8. Another somewhat common one in the past, which you still may come across in older PLC systems, would be hexadecimal, which that's base 16. So that's kind of an interesting one. There, any single character can be 0 through 9, or then continuing on, A through F. Sorry, there. So you would count up, let's say you're starting counting like you're used to in base 10, you'd go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you just continue on, A, B, C, D, E, F, before you would have to go on to the next character. So you can see hexadecimal is the first one we've talked about that has a higher information density than the decimal base 10 that you're familiar with. Okay, so that's a quick introduction to a number of different number systems: base 2, base 10, base 8, base 16. To start with, now we're going to focus a little bit more on binary. That's where we have just 0 or 1, because really all of these in computers are going to get reduced down to binary at some point. We said at the hardware level, there's really only on or off. There's not, on, 25% on, 50% on, 75% on in an actual switching transistor inside the processor. So for logic, it's just simple to just have ons and offs. It's simple, it's easy to do hardware-wise, but it makes it so that we need to use more memory to store the same number. You can kind of see that as we looked at these different systems here. But let's focus on binary for a minute. So binary, we said, is base 2, either on or off, which that's going to be really applicable in PLCs for what we call our discrete inputs, where we have an input that's either on or off. Later on, we'll have to get into how do we deal with the values that aren't just on or off. So you can turn a motor on or off, but if you want to control the motor's speed from 0 up to 100%, but not only 0 100%, you're going to need a system other than just on or off. And that's where we get into analog values. And we'll also then have to have different number representations. But we'll focus on binary for now. So binary can also be called Boolean because of the type of logic that you can use using binary values of 0 or 1. So the smallest piece of information in a binary or Boolean system, we call that a bit. So if we have just one position, that's 1 bit. And it can be either, like we said, a 0 or a 1. So there's 2 potential values in that bit. So that's our most fundamental building block of numbers or memory in a PLC is the bit. Obviously we're going to need more than that, so we start stringing them together, and if you put together 8, 1, 2, 3, 4, 5, 6, 7, 8 bits, then this 8 bits becomes what we typically call a byte. So 8 bits, so we'll just number them here, 0, 1, and this is another thing where you start numbering from kind of matters. So I'm going to start from 0, so I'll say 0, 1, 2, 3, 4, 5, 6, 7. So the 0 bit through the 7 bit. So 8 values makes up 1 byte. Then if you string together 2 bytes, I'll just approximate that out here, we call that a word. So this is byte 2, this is byte 1. So if you have 16 bits, we would call that a word. And then continuing on, if you want to expand that, if you have 2 words, we usually call that a double word. So 32 bits would be a double word. And if you go 4 bytes or 64 bits, that would then often be called a long word. So those are all different ways of collecting bit or Boolean information. When they're referred to as this, they're typically, even though they're 64 bits or 32 or 16 or 8, depending on which chunk we're looking at, if we're referring to them as that, we're still considering them binary data. We're looking at the value of any individual bit within that word. We're not typically calling them that if we're looking at a value that's encoded in multiple bits of that byte, word, double word, etc. Let me explain what I mean there by kind of exploring the next concept. So we can use the same number of bits to represent things other than ones and zeros, and that's what I was talking about when we want to get into an analog value, a other than on or off kind of concept. We're going to get into representing numbers. And just if you think back to math class, kind of one of our most basic types of numbers is an integer. So let's review what an integer means. Integer means a whole number. So the number 2 would be an integer. 2.25 is not an integer. That's not a whole number, right? It's 2 and a quarter more on your way to 3. This would not be an integer. The fraction 7/3 would also not be an integer, right? It's not a whole number. So integers are valuable if you're counting something that always occurs in whole units. So say you have a machine and you're counting the number of processes that it's gone through, how many pieces have moved through. That's going to be an integer number. You're unlikely to move through 2 3/4 parts. You're going to have moved through 2 or 3 parts. So integers can be useful, but again, there's lots of applications where it's not going to be useful, where you have some gradation finer than whole numbers. So we need to get beyond just integers. And the next step from that would be what's called a real number. So real would be a number that has a decimal point in it. So coming back up to here, 2.25 would be a real number. You're going to represent both an integer component and then a fraction, and you're going to have a decimal point that you're communicating somehow it is. So because you can represent that, if you think back to scientific notation or exponential, you can express a large number, a wide, infinite number of values by changing what exponent or power of 10 you put after it. So real numbers happen when you need more than an integer. So let's talk about number representation in these systems. We talked about what integers are and what real numbers are. Within integers, we can have different ranges that we can list a number, right? So if you think back up here to our binary numbers, the kind of basic block, smallest block we had was a byte. So in a byte, we have 8 different positions. 1, 2, 3, 4, 5, 6, 7, 8. And each of those can be either a 0 or a 1. So at our most basic, we would have this, let's say this rightmost is our least significant bit. If we can have 0 or 1 position, we're representing 2 values. So if we have just 1 bit, that can equal 2 values. Let's take a look at what happens if we have 2 bits. We have 1, 2. This can be either 0 or 1. This can be either 0 or 1. So now we have 2 values in each one times 2. So in this case, 2 bits can hold up to 4 values. So in this case, if let's just look at some examples of that. If we have 0 and 0 in those 2 spots, that's going to equal 0. Then let's switch the first bit to 1. So now if we have 1 and 0, we would represent that as a decimal 1. And then we could put 0 in the first, 1 in the second, and that's going to be equal to our 2. And then the last option we have would be 1 in both positions, and that would be 1 plus 2 equals 3. So you can see there in 2 bits we have 4 possible values, 0, 1, 2, and 3. So a way to mathematically quickly tell how many values you can represent with a number of binary places is the equation is 2 to the n, for n being how many number of places. So if you put in there 2 to the 1, if you only have 1 bit, you're going to be able to have a value of 2. So let's just write that down. 2 to the 1 equals 2, and then if you do 2 to the 2, if you have 2 bits available, that's going to be 4 potential values. Continuing on, 2 to the 3, 2 times 2 times 2, you get the idea. There you would get 8 potential values. So you can see with each bit you're doubling the numbers you can represent, and that makes sense because each bit can have either a value of 0 or 1. So an increase by a power of 2 each time. So let's expand on that and see what we can do, how many potential decimal numbers we could represent in an 8-bit word. So using our equation that we came up with there, we can plug in that 2 to the 8th is equal to, grab a calculator, 2 to the 8th is equal to 256. So we can have 256 representations. And you'll remember that if we're starting at 0, that means the numbers we can represent would be 0 through 255. And you can do the same thing for if we had 2 to the 16th. I'm sorry, I wrote 250 there. That was sloppy. 256. So do the same thing again. 2 to the 16th. And we can get 65,536. Which again, just trying to help you think about these things, what often throws people is I can't actually represent 65,536 if I'm starting at 0. This would actually mean there's a range of values from 0 to 65,535. If I actually wanted to represent 65,536, I'm going to need 1 bit more than the 16 I had here. Okay, so taking this information, looking back at our data types, so in a byte we said we can have 256 values, in a word we can have 65,536, etc. So that would go on and on. We call them different data type if what we're representing is numbers instead of binary values. So we had a byte of 8 bits when we were looking at each of those bits as its own independent representation of either an on or an off. If instead we're looking at that 8-bit value as a representation of a number, we would call that a short integer. Or that's usually abbreviated to a SINT. So that is an 8-bit binary representation of a number. And so short integer, 8-bit. If it's just labeled an integer, we would say that's 16-bit. And just like we had double words, we can have double integers and long integers that are 32 and 64 bits respectively. Okay, but those are all still integers. They're going to be whole numbers, and you can have negative integers if that's of some use to you mathematically, but you can't have fractional integers clearly. So we said that if we need to represent fractional numbers or real numbers, that data type is called real. And we won't get too much into that right now other than just describing what it is. Called real. Sometimes they're called floating points, and they typically take up 4 bytes of information. So 32 bits is usually the smallest real number, and they can be longer than that. They could be twice that at 64 bits. So with binary, bit, integer, real, those data types we've kind of covered are numbers or on and off, but there's more complicated things we can want to represent in a PLC as well. Example, that might be a text string. We haven't done anything in here that would refer to text. There's also some more complicated data types that are built up out of different pieces that might involve multiple integers or values in them. And those can vary from PLC manufacturer, from one to another. But some common ones would be time types. There's other custom data instructions that are built up out of these basic elemental type instructions or variables. So one of the most common ones, like I said, would be a string representation. So think anytime you're talking about text, we typically call that a string type. And going way back to when they were first kind of developing computer systems, they have developed a number of standards of how they would represent text using digital data. Because remember, all of these systems at the hardware level are going back to zeros and ones. So they set up a standard code for English representation that's called the ASCII code. You can look that up if you want to know more information about that. But it's basically a way of using ASCII, I believe, is a 7-bit base. So within that 7 bits, let's think about that using the information we just learned. We said it's 2 to the 7th. So if we look at that, that would be 128 potential values. So that's plenty, right? Because in English we would have 26 letters, and then we can have uppercase and lowercase letters, and then we also have numerals 0 through 9. We also have punctuation. So 128 gave them some space to handle that. Let's look at what if they'd gone down one level and done a 6-bit code to represent that. What that would have been 2 to the 6 would have been 64. So if they only had 64 potential values in that character set, you can see they would have run out pretty quick. If we have 26 letters, if you want to have both upper and lowercase, you're already at 52. You add in numbers, you're going to 0 to 9. You have hardly anything left for punctuation or control. So you can kind of just start thinking through, how do we decide how many character spaces are we going to need to represent information. So I'm going to show you what the ASCII table looks like here real quick. So this is a representation of the ASCII table. So group got together when they were moving from teleprinters basically to electronic communication, and were agreeing on a binary representation for the English language. So as you look at this, you can see this kind of teal row of characters. That is the English language characters, English alphabet, numbers 0 through 9, some punctuation, and then there's a bunch of what we would call control characters that are not something that's printed when received as information, but are useful as returns, escapes, backspace. You get the idea. Control characters and then printable characters. And so if we look at these are represented by binary values. If you count through there, you'll see that there are 7 binary positions required. So if you have all ones, that's the delete key basically. On the other end, if everything is 0, that's a null. So we can look at the letter A. The lowercase letter A is 11000001. Uppercase letter A, 1 and 1, with zeros all in between. And kind of useful thing to look at while we're on this chart is it includes not only the binary representation, but also the decimal, the hexadecimal, and an octal. So those are all different number representations of the same English character. So it's kind of another nice way to look at the different ways of representing the same value. So you can see here down at when you're at lower decimal numbers, the decimal number 3 is same in hexadecimal and in octal. That continues up until you get to the value 7, and you can see that once you roll over to the 9th digit, or number 8 in octal, you have to go up a space. Whereas in decimal and hexadecimal, we can keep going with one character or one place until we get to 10 in decimal. But you can see hexadecimal, you keep carrying on with only one place used all the way until you get to 15, or the 16th value. So you can see in order of what I guess I would call information density, the highest density is in hexadecimal, then decimal, then octal, and then you can see binary is quite a bit less. So all different ways of representing the same information. But we were looking at this mainly to talk about how do we represent text information in a binary format. And so that would be using, for the English language, we use the ASCII character table. Okay, so that table had the overview of how we represent English characters in text. So you can see that it's going to take, basically we don't divide things into 7-bit words, so we have 8-bit words, so it's going to take at least 1 byte for each character. And we put those bytes together into a long, what we call string. So anytime you see the string data type, you can think we're talking text-based. As I mentioned, another common data type is a time value, and time is going to be made up of numbers, integers typically. But if you think about it, time is not just a number, right? It's not a base 10 decimal number. It's a base 60 for seconds, and then if you go down from seconds, you're going to have milliseconds or thousandths of a second. So it doesn't have a uniform base that you can easily represent it as. So we usually have a custom time data type that has particular syntax. And we'll get into that more in a future lesson, but just know that time is not just a simple decimal number. You have to make clear, am I talking about, let's say if you had a time value variable that had the number 37 in it, you need more information to know, is that 37 seconds, 37 hours, 37 milliseconds. You could think in days. Typically by the time we get into days, then we're talking date. That's another custom or more complicated variable that has pieces built into it, both a value, and you need to communicate what units you're talking about when you say time or date. So that's enough overview of the different data types, but let's do a couple conversions and just expand a little bit about how do you convert between binary, decimal, octal, hexadecimal, that kind of idea. So let's start with a decimal number. Let's do something small to start with. Let's say the decimal number 5. And first we want to represent that in binary. So if you think back to binary, it's going to take obviously more than one place to represent the decimal number 5, because in binary we said that each place can represent 2 values. So if we wanted to figure out mathematically how many places it was going to take, we could just go through the list. 2 to the 1, that would have been 1 bit. 2 to the 2, we're going to get 4. Still not quite there. So we can see it's going to take at least 3 bits for us to represent the number 5. So we can say, I like to think of it like this. This is the 1's position, this is the 2's position, and this is the 4's position. So to get the number 5, do we need a 1, a 2, a 4? Yeah. So we're going to add together which of these numbers equal 5, and that would be a 4 and a 1 would equal 5. So in this case, 4, 1, that's decimal 5. Let's do another one. Let's say decimal, let's say the decimal 12. Okay, you can see it's going to take more than 3 bits because we got up to 8, and you can see the pattern here. When we go to 4 bits, hopefully you can see that we're going to be able to represent up to 16 values. So I'm just going to write out here my 4 positions. And again, this is 1's, 2's, 4's, and 8's. So looking at those, you just got to start kind of thinking down which of these would I need. So it's pretty obvious here. We're going to need an 8 and a 4 and 0, 0. So 1, 1, 0, 0 in binary is equal to decimal 12. Okay, let's try a different system, not as common, but still a good practice to kind of think through how it would work. What about we take the decimal 12 and we want to represent it in hexadecimal. So decimal equals 12, and we want to know what is that in hexadecimal. And if you remember, I said hexadecimal is base 16. So this is kind of one of those situations where typically we're so used to thinking in decimal that it would take at least 2 digits to represent the value 12. In hexadecimal, we can really actually represent that in one character space. If you think back to how I showed you we count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I kind of start writing at 9 to help myself remember. We go 9, and then for 10 we go A, B, C, D, E, and F gets us up to 16. If you think of this as 10, 11, 12, 13, 14, and 15, because we're going from 0 to 15, that would be 16 values. So in this, to represent the decimal value 12 in hexadecimal, all we have to write is one character, C. So again, probably won't see it too often, but you used to see it quite a bit in PLCs, and so it's useful information to know. If you think back to the ASCII chart too, it represented information in both decimal, hexadecimal, binary, and maybe one other one. I can't remember what all was on there, but those are all. That was a good example of how you can use multiple different representations for the same value. Okay, I think that's enough on data types, data representation, number systems. We'll get more into that as we need to throughout the term, but this is a good overview of how computers, PLCs, etc. represent information, different types of information. So we talked about binary information. That means it's just on or off, a 1 and 0. We also talked about integers, so those are a number representation. Again, at its base level, it's still a binary Boolean on or off, but we group them together in ways that we agree are going to represent information. Integer information, so whole numbers, and then if we need floating point information, decimal point, basically rational numbers that have fractions, that kind of thing, then we would use a real or floating point type. And then we touched on more complicated things like time, where we need to have both a value and a unit system communicated through the through the variable, and then string type data, where we're representing a language. So in our case, typically English, but the exact same process would apply for non-English languages. They have to be represented by an agreed upon binary data value. So hope that helps, and we'll talk more about that as we start assigning variables inside the PLC this week.